Yeah, we can hear you. You can try to share your slides.
Share the screen.
Pietro, okay. You can begin, okay.
Is it sharing?
Yeah, it's shared, but probably it's better to make it full screen. Yeah, no, perfect.
Okay, I can start. So I will show the results of a purely data-driven study of quarkonium data from Atlas and CMS. In first, I will look at the case of proton-proton collisions, where I will show that there are very simple patterns of scaling of cross-sections as a function of mass and momentum. And then, using this as a baseline, I will give a look to the case of lead-lead data to see if we can interpret them in the framework of the same scaling seen in proton-proton collision with some minimal modification. And we will see that this will give a nice evidence of the sequential suppression mechanism. The first indication of the data is that there is almost universal scaling of the cross-section with the variable which is the ratio of PT over M. So these two plots are at 7 TeV and 13 TeV, the cross-section of all quarkonium states measured at Atlas and CMS. And they are plotted not as usual as published as a function of PT, but as a function of PT over M. If we do this, we see that all these spectra become parallel to one another. These fitting curves are one curve simply repeated over and over.
Is it power-like or exponential decay?
It is a sort of power law. At high PT, it becomes a power law. At low PT, it has some. It is the usual function that it is used in the literature. It was used by Arabi the first time, but I don't know. It is practically almost a power law, but it has some turn down at low PT. But it is a purely empirical function in any case. Here we see again the same data on the left, collapsed all to the same normalization, but separately for 7 and 13 TeV. So you see that we can also recognize a small difference between the slope at 13 TeV and 7 TeV. And to see the agreement with the data, we have also plotted here the pools. So they are good. And so there is an evidence of the fact that after making this dimensional scaling from PT to PT over M, at least for PT over M bigger than 2, even if things are not so bad even below, there is no hint of mass dependence of these PT over M distributions. And this from J psi to Y3S. So there are 7 different states. And here we make, on the left plot, we make a zoom, so to say, to the case of chi production, because we plot the ratio of chi C2 over chi C1, chi B2 over chi C1 as a function of PT over M, and also the ratio chi C over J psi measured by Atlas. And you see that they are completely flat. So this is another visual confirmation of this PT over M scaling. On the right, we give a look also at the polarizations, which are not in contradiction with this universal momentum scaling, because you see that the polarizations are all close to 0 for Y1S, psi2S, and J psi, which have a very different feed-down contribution from chi states, Y1S 40 or even 50%. The psi2S has 0 feed-down from chi states, and the J psi 25%. So this also implicitly contains the information that the chi states do not perturb this universal scaling. In this following slide, we see the mass scaling now, the scaling with the mass. First, we have seen the scaling of the shapes of the spectra. Now, let's see the normalization of the distribution. In particular, let's look at the J psi and epsilon 1s, which are the closest states to the fundamental state, to the closest to the mass. The masses are the closest to the simple double of the mass of the heavy quark. And in green we have the 17 TeV case, in blue the 13 and 7 TeV case in green and blue. So the ratio, we parameterize the ratio between J psi and epsilon as a power law in the ratio of the quark masses. And if we do this, we find that the power is, the exponent of the power law is 6.6 or 6.5. It's 7 TeV, 6.6 plus minus 0.1. It is practically identical the two energies. So what does this 6.6 mean? To understand better, we look at the case of Drelian, which is a very well-known example. Here on the left, we have the measurements of Drelian cross-section by CMS and Atlas in 7 or 8 TeV. For the corresponding power law in the masses is 3.6. For the quarkonium, we had 6.6. But from dimensional analysis, we know that for Drelian, the cross-section a function of mass should scale like m to the minus 3 plus beta, where beta comes from the Parton luminosity factor, which is the ratio of square root of s divided by m to the beta. So beta comes out to be, from the Drelian case, around 0.6. And so, in fact, we have that for Drelian, at partonic level, the scaling is m to the minus 3. Correspondingly, we can subtract this partonic factor from the case of quarkonium and find that the scaling is 10 to the minus 6. So the difference between quarkonium and Drelian is an integer of 3 in the scaling with mass. And this 3 is intriguing because it is identical to the dimension of the bound state wave function, which is what is missing in the Drelian case. And let's now have a look at what all these scalings that we have observed imply. But before this, let's start from a completely general parameterization in which we put around things in a way that will be convenient afterwards. But for now, this parameterization is fully generic and even redundant. So we parameterize the quarkonium production cross-section as a sum of several terms. Each term has a L and F function. These here they are completely general, but they are made written in a way that they resemble the long-distance matrix elements of an RQCD. In fact, L is divided by m3 to the third, so L has dimension of energy to the third, dimension of the bound state wave function of S wave quarkonia. Then we have also the Parton luminosity factor that we have seen before, and the global dimensionality factor mass to the minus 3 again. So for now, this is a completely general function because L and F are completely general functions of all variables. But now let's apply the observations that we have seen in the previous slides. First, the PT over M dependence is universal, identical for all states. Therefore, it is not dependent on the mass of the heavy quark, nor on the mass of the individual state. This is a nice evidence of the factorization between short and long distance effects. In particular, we can apply it to the above formula by rewriting L as something not depending on PT over M and F as something not depending on the masses. So we have this intermediate step here. Then we applied the other observation that the normalization of the cross-section from germanium to bottomonium, scale like the mass of the quark to the -6, and it has no apparent energy dependence. So this means that the factor n to the -3 times n to the -3 that we have here at the beginning of the formula is sufficient alone to describe all the required quark mass dependence. So L should not have any further mass dependence inside. Moreover, it does not depend on the energy, because this mass scaling is energy independent, has been seen to be energy independent. Therefore, we can reduce this L to a dependence on of only the masses and only on the ratio of the masses, mass of the state divided by the mass of the quark. The final formula is this formula, which now, yes, it resembles fully a factorization formula. We have a factor that depends only on the ratio of the state over quark mass, a factor that contains all dependence on Pt over m rapidity times the luminosity factor and the further the dimensional normalization factor, which is the dependence of the quark mass. We want to use this to reach our final step. Now it is only one slide away, but first we want to do one thing. We want to extrapolate the cross sections to two ideal cross sections of the when the mass tends to twice the mass of the heavy quark. To do this, so we have in this picture the all cross sections in two different, split in two different scales. On the left we have germanium, on the right bottomonium. So you see that we have nanobarns on the left, picobarns on the right. And the continuous black line is simply the mass dependence, the m to the -6.6 that we've seen before, result of this -6 plus the 0.6 of the partonic luminosity factor. Then we do a further, we do a fit to make the extrapolation of the quarkonium cross sections, to extrapolate until we intersect this black continuous line. And these points of intersections are our cross section for mass, for an object which has the mass equal to twice the mass of the heavy quark. So this is it is interesting to note that the behavior of the bottomonium and of germanium are completely compatible. So we can fit these two blue and yellow curves as one curve with one power law parameter. So, but from this plot we obtain therefore the two cross sections extrapolated to twice the mass of the heavy quark. And in the next slide we finally see the central result, which is this. Here we see the ratio of the quarkonium cross section over the cross section of this extrapolated cross object having twice the mass of the quark, and we plot them as a function of what we call the binding energy. You know, there are several definitions, but this definition is the difference between the threshold energy necessary to produce two D meson or two B mesons minus the mass of the quark of the quarkonium. And if we do this plot, we see that we obtain exactly the same plot almost for the two energies, 7 TeV and 13 TeV, and above all states are completely aligned along the same line. We can parameterize this ratio of quarkonium cross section over QQ bar cross section as a power law in the binding energy. This exponent delta, when it's fitted independently, always gives the same result, 0.63. This is a nice confirmation of the fact that the dependence on the bound state mass is a purely long distance effect, which is completely factorizable from the momentum dependence of the cross sections in the laboratory. And we will use this as our baseline for PP production. And we will introduce now a further hypothesis to see what can happen in lead-lead collisions. First, we'll do an important parenthesis. We can assume that this was done for S-wave states. We can assume, because in the absence of other, simply because it is the simplest possible assumption, not for other reasons, that we have exactly the same behavior also for P-wave states. So we will assume that also for P-wave, we have this dependency on the binding energy with the same power law. If we do this, we can produce automatically all possible feed downs between any states, even the most sophisticated ones. And we will use all this feed down structure in the following study of the suppression of the states in lead-lead collisions. First, with this only note to check that this feed down structure that we've used is not incompatible with the existing measurements, which are from LHCb, but they are only in a different domain. They are at the forward rapidity. While in all this study, we are using only mid-rapidity data. In any case, this can be seen as a confirmation that nothing is very wrong. Now, so let's address the nuclear modifications of the production in lead-lead collisions. We want to see if there is a minimal modification of the scaling rule with binding energy that can describe the data in lead-lead collisions. We are in particular interested in a plot like this. This is particularly intriguing. This is the ratio of the nuclear modification for psi2s over the one of J psi. And it is interesting to see that this ratio goes immediately to much lower than 1 without passing through intermediate value. So it is never 1. So at the lowest possible value of number of participants, we have already a very strong drop of psi2s production with respect to J psi production. This suggests that there is some kind of threshold effect, because psi2s is characteristic for having a very small binding energy. And this is the base idea of the model that we will propose. But first, let's say that we will look at this kind of data. We have data as a function of binding energy. Here we can see on the left that the dependence of binding energy is not monotonic and not very trivial. We have psi2s, then we drop to epsilon 2s, 3s, we grow a bit to epsilon 2s, we go above J psi, and then more or less at the same level epsilon 1s. And then we will also look at the centrality dependence of the RAA for all states. The states except the epsilon 3s for which there are no measurements. So the model is this. While for PP collision, we have this simply the power law in the binding energy with delta 0.63. For PP, we will assume this slightly modified power law. We introduce a shift of energy, delta E. This means the motivation is this, that when for increasing delta E, it becomes less and less probable to form the bound state. In particular, when delta E tends to the value of the binding energy or even bigger, the QQ bar will not transform into quarkonium, but rather will transform in something else. So this empirical pattern, this is a purely empirical pattern determination. By itself has no special meaning, but it can have a physical interpretation. In particular, it can have two completely different interpretations. In one case, we can associate delta E to the mass, to the energy of the threshold of the production as a decrease of the threshold energy. So this would be a screening effect. The threshold energy is reduced, so it becomes easier for the QQ bar to transform into mesons rather than into quarkonium. The second possibility is that delta E is associated to the mass of the quarkonium, so it is like an increase in the mass of the QQ bar. This can be a multiple scattering effects, which increases the opening angle and therefore the value of the invariant mass. And this is an hypothesis that was discussed already in the past. In any case, for us, it is a purely empirical description. Before going to look at the data here, there are no data yet. Let's look at what these formulas mean. It is an example of RAA calculations using these formulas as a function of binding energy for 3 different values of this shift delta E, increasing from green to red, and one, I don't know if I spoke about this. Oops. I think I dropped, no, I skipped the one slide, which was this. So we have delta, so in this model, delta E will depend, we will assume that the delta E depend on centrality. That is, this effect will be bigger and bigger with increasing centrality. It is 0 in proton-proton collision and increases with increasing centrality. And besides delta E, we also introduce another parameter, sigma delta E, because actually we assume that delta E is not one fixed number, but it is a distribution of energies. And sigma delta E is the width of such distribution. And for simplicity, we make 2 very strong assumptions: that delta E is identical for all states, quarkonia, charmonia, and bottomonia, and in sigma delta E is even independent of everything. So it is one parameter independent of centrality and conditions. Then we will fix delta to the value found for the proton-proton collisions. And we will consider all states, psi, chi's, and upsilon, and calculate first the suppression for the directly produced states, and using also all branching ratios from the PDG, we will calculate also the promptly produced states, considering all feed-down chains from P to S waves, from S waves to P waves, and even the chains. And this, again, it is one example of these calculations with increasing delta E. You have the continuous line, which is for directly produced states. They are continuously because they are simply function of the binding energy. Then for each actual and physical state, we calculate the effect of calculate the prompt cross-section, which can be done only explicitly for the specific states, because then we consider the specific feed-down structures and the specific branching ratios. You see that the feed-down effect is especially big for the upsilon 1s, which drops the array a lot, and the second biggest effect is for the psi. And now let's also compare a bit, make a first rough comparison to data, fixing the 2 parameters of the model, delta E and sigma delta E. We obtain the directly produced curve, and the symbols, the red symbols are the ones that have to be compared to data for the prompt production. You see that they are compatible with the data, and they reproduced with this non-monotonic behavior. Now we can do a fit of the data. We will consider the data of CMS and Atlas at 5 TV. There are 37 data points, which are the one in the top plots. For RAA is a function of number of participants. We have and we assume a dependence of delta E on number of participants. We do this with this function. We assume a linear dependence on the logarithm of the number of participants, because we tested several dependencies, and this is simple and gives a good result. So 2 parameters of the fit are these coefficients of this linear dependence of delta E And the other parameter of the fit for the total of 3 is the sigma of the distribution, which is constant for all centralities. And all this is then, this parameterization again, I repeat, is identical for all states. And we see that we have a good agreement with the data. We have no data for the upsilon-3s in green. And also interesting, we can give a look again at this double ratio psi to s over j psi, which has this sudden drop at the very low number of participants. So this threshold effect, which is embedded in this simple model, reproduces this physical effect, which was almost the starting observation that motivated this. Then we can look at the same thing as a function of binding energy. Here, the gray bands are the direct production cases. Then what we have to look at for the comparison with the data are the colored bands, which are only segments, obviously, and at the specific values of the physical states corrected by all relevant feed downs. And you see that in several bins of a number of participants, we have always a good agreement. So this is already the summary. We have seen that considering mid-rapidity data from the LHC, we see very interesting scaling rules that make the experimental scenario particularly simple. For the proton-proton collision, we see that the shapes of the T distributions scale like Pt over M. The normalizations scale with the mass according to the binding energy. And this is a very nice picture because it is a factorized picture that mirrors very well NRQCD, but not only, any model in practice that tries to describe quarkonia production. And in a lead-lead collision, we try to make a very simple and minimal extension of what we saw in proton-proton collision, adding simply one quantity, this shift in energy, in binding energy delta A, which makes less and less probable to form the bound state. And this gives another scaling variable for the lead-lead case, which is binding energy minus this delta A. As a last slide, as an outlook, I would like to say that.
Okay.
And I would like to comment on this slide, but it just disappeared, and I don't know why. I don't know if you can still
we can see only a black screen, so no your slides. Unfortunately, try to now it's okay. Yeah.
Okay. And I want to see that it is possible. Okay, I will go this. It is possible to make predictions also from in this model of the lead-lead collisions that were made. One interesting prediction is that the most suppressed states of all should be the Chi-C states, Chi-C and also the Chi-B2P, okay, together with the upsilon-3s, which is already known to be very strongly suppressed. In fact, it has never been observed. And the least suppressed states should be, besides the upsilon-1s, the Chi-B1P states. So this means that with respect to the 1s state, it should be easier to observe the Chi-B1P with respect to the Chi-C in lead-lead collisions. In fact, the Chi-C over J psi ratio should drop to 30% from proton-proton to lead-lead. Instead, the Chi-B over upsilon-1s ratio should remain almost identical from proton-proton to lead-lead and almost have no dependence on centrality. So this is only an idea to try to look at Chi-B production in lead-lead to see, also to check this binding energy hierarchy. Okay, now finish.
Okay. Thank you.